Hi. I want to give some examples where I'm starting with a power series and I'm going to find a closed formula for the function that I've got based on Maclaurin series formulas that I already know. So for these problems, I'm going to be basing my work on 3 Maclaurin series formulas. One of them is that the exponential function, e to the power x, can be written as a power series, the sum from n equals 0 to infinity of fractions x to the power n divided by n factorial. This will be one of my common Maclaurin, This will be one of my common formulas that I'm using today. Another one is that the cosine function can be written as a Maclaurin series. Again, the sum from n equals 0 to infinity. But because the cosine function is an even function, I'll only have even powers of x showing up in the series expansion. So my sum ends will have the formula minus 1 to the power n times the number x to the power 2n divided by 2n factorial. So I double n and I take the factorial of whatever that number is. And third, I'll have the sine function. So similar to the cosine function, the sine function I know is an odd function. And when I take the Maclaurin series, I'll only have odd powers of x showing up. This is an interesting property of power series, similar to polynomials. In polynomials, if I know I have an even function, only even powers of my variable are going to show up. And if I know I have an odd function, only odd powers of my variable are going to show up. And this is also true for power series, at least as long as they're centered at 0. The other nice thing about all 3 of these Maclaurin series is that each of them has an infinite radius of convergence. So these formulas are actually valid for all real numbers. It's a pretty cool property. Now, to get to the problem set, the first series I'm going to look at is the sum, n starting at 0 and going to infinity. And here I've got fractions with numerator x to the power n, denominator 3 to the power n times n factorial. I'm working in a bit of a limited context here. So my goal is that I will rewrite this formula to make it look more like one of those other Maclaurin series. Well, I don't have that alternating sign, right? I don't have that minus 1 to the power n. And more than that, I see that my exponent on the variable x can be any non-negative integer. It could be 0, it could be 1, it could be 2, it could be 3, and so on. So I don't expect that the cosine or sine expansions would be able to help me with this problem. Now, to make this look more like the Maclaurin series for the exponential function, my denominator is just supposed to be n factorial, and my numerator is supposed to be some number raised to the power n. Well, to make everything match, I'll say what all has exponent n in this problem. Well, there's an x in the numerator, and there's a 3 in the denominator. both of those terms have an exponent of n. Okay, well, now that I've written this as some quantity to the power n divided by n factorial, that's the formula for my summands, and I'm adding all of these up starting at n equals 0 and going to infinity. Well, ordinarily this would give me the Maclaurin series for the exponential function, only here I've divided x by 3. So this will be the Maclaurin series for the function e to the power x over 3. All right, let me try another one of these. In this problem, I will have minus 1 to the power n. So I need to specify my n starts at 0, and I'm looking at an infinite sum. My summands have the formula minus 1 to the power n, x to the power n, all divided by n factorial. Well, this one might be a little deceptive. Both the sine and cosine Maclaurin series have minus 1 to the power n in their summand formula. However, they only have even powers of x for the cosine series and odd powers of x for the sine series, where this formula does not put that restriction on my exponents. This n could be either parity, even or odd. So I'm going to gather everything up that has that exponent n on it. There's a minus 1 to the power n, and there's an x to the power n. So I can say this is the same result as taking the number minus x and raising that to the power n, dividing this whole term by n factorial. This is very similar to the previous problem. I had to use a little bit of thinking here to justify what I was doing with this manipulation, but what I wrote here is true from an algebraic point of view. I can either raise two things to the power n and then multiply them together, or I could multiply them together first and then raise that product to the power n. Either way, I get the same result. Writing the formula this way, though, tells me that I'm looking at the Maclaurin series for an exponential function. And this time I've got e to the power minus x. So whatever I do to the variable x inside the Maclaurin series, I need to do to it in the closed formula as well. Whatever I do to one side of the equation, I do to the other side to keep things balanced. Well, let's continue. Let's look at a sum n equals 0 to infinity, minus 1 to the power n times x to the power 2n plus 2, all divided by the term 2n, which has been factorialized. So this resembles the cosine Maclaurin series very closely. The exponent always produces an even number. The denominator is always an even number, which I've taken a factorial of, and I have this minus 1 to the power n business. The only problem that I see then is that my exponent of x has this extra plus 2. Now, to make this look more like the cosine series, I'm expecting to see minus 1 to the power n, x to the power 2n, all divided by 2n factorial. But these two sides aren't balanced yet. What's missing? Well, if I have plus 2 in this exponent, I can break that off and say that I've multiplied my summand formula by x squared, right? I'm just using laws of exponentiation. And here is a place where I'm going to do something that is easier to see if this wasn't in sigma notation. So I'm adding up all of these fractions. The exact formula of the fraction is going to change based on the number that my index n is representing. For n equals 0, I'll get a certain fraction. For n equals 1, I'll get a different fraction. For n equals 2, I'll get a different fraction again. And then each of those fractions is multiplied by the same x squared. How do I know it's the same? There are no n's in it. So the value of n does not change this multiplication by x squared. So for the fact that the x squared term does not have an n in it, I can factor it out of the sum. So what am I doing here? I'm using the distributive property of addition. It just looks a little bit different in the context of power series. So my sigma notation has sort of obscured what I'm doing here, but I'll say that each of these fractions, no matter what n is, has an x squared that I can factor out, and I will do that. Now I have to be careful that the series that I've got left over still converges. But now the sigma notation is exactly the Maclaurin series formula for the cosine function. And from what I was saying earlier, this will converge no matter what value x is. The Maclaurin series for the cosine function has an infinite radius of convergence. It's valid for the whole number line. So this series that I've got here is the Maclaurin series representation for the function x squared times cosine of x. Let's look at another example. If I can clear the screen, there we are. I want to take the sum, n starting from 0 to infinity, and I've got minus 4 to the power n, x to the power 2n, and this is all divided by the number 2n factorial. Okay, well, once again, this resembles the cosine function. I have a negative thing to the power n, I have x to an even power, I have an even number inside the factorial function. Well, the difference now is I've got this minus 4 to the power n. Once again, I want to rewrite this so it more closely resembles the formula for the Maclaurin series of cosine of x. I'm expecting to see minus 1 to the power n. I'm expecting to see x to the power 2n. I'm expecting to see that denominator of twice n inside the factorial. Now, I need to keep this equation balanced, so what am I missing? I'm missing that 4. Algebraically, what I'm doing is I'm splitting this product. So if I take the number minus 4 and raise it to the power n, well, I can take the numbers negative 1 and positive 4, raise them each to the power n separately, and then multiply back together. Both of those operations will give me the same value. Okay, let's take a look. I've almost got the formula from the Maclaurin series of the cosine function. For is raised to the power n. And that's my discrepancy here. That's my difference from the formula I'm expecting to see. Because it's raised to the power n, the exponent will be different as the index n changes. I'll get a different power of 4 when n equals 0 as compared to when n equals 2 or when n equals 7. Always get different powers of this number. So I will not be able to distribute and factor the way I did on the previous example. Now, I remember back to when I was grouping things with my x, and that was a pretty successful technique. So maybe I can group this 4 to the power n with my x to the power 2n. That's a nice idea, but if I want that grouping to be algebraically valid, I need both of those quantities to have the same power. So as an intermediate step, I'm going to rewrite this. I'm going to keep everything that's in the cosine Maclaurin series exactly as I had on the previous line. I'm going to change my 4 to the power n. I would like this to be an exponent of 2n instead. So what number can I put here and have it still equal 4 to the power n? Well, that's going to be 2. Because 4 is the square of 2, taking 2 to the power 2n is the same result as if I took 2 and squared it first, producing 4, and then raising 4 to the power n. All right. Now, what this does is I have written my formula where I have 2 quantities, both to that same power, both to the power 2n. And in my third line here, I will combine those things. So the -1 to the power n is staying the same. 2n factorial on the denominator is staying the same. And now I'm saying I'll take the quantity 2x and raise that all to the power 2n. Well, cool. Now that I've got the formula written this way, I can say that's obviously, depending on what you consider to be obvious, but that is definitely the Maclaurin series formula for the cosine function, but I doubled x. And if I'm going to double x inside my Maclaurin series formula, I've got to double x in the cosine as well. So this is the Maclaurin series for the function cosine of 2x. All right. Now for my last one of these examples, I want to look at something a little bit different where I'm not necessarily doing algebraic manipulation. This time I have the sum of -1 to the power n, x to the power 2n plus 1, all divided by the number 2n plus 1, which I am then going to put inside the factorial. The only difference is that now I'm starting my sum at n equals 1 and going to infinity. Still an infinite series, but my index starts at 1. Other than that, this looks like the Maclaurin series for the sine function. Well, what has happened here? Let me think about the terms that this produces. The very smallest one of these is going to be my index n equals 1. My -1 to the power 1 will be -1. My numerator will be x to the power 3. My denominator will be 3 factorial, right? So I'm just writing out, oops, got a little bit bigger there. I'm just writing out what that formula would give me. If n equals 2, I'll get a positive number, right? -1 squared is positive 1. This will be multiplied by x to the power 5 and divided by 5 factorial. And then I'll continue. I'll have minus x to the 7th over 7 factorial and plus x to the 9th over 9 factorial and minus x to the 11th over 11 factorial. That's going to continue following the same pattern that I expect to see from the sine function. All right. Well, let me write out the Maclaurin series for the sine function, and I'm going to write it out using my ellipsis rather than the sigma notation. The Maclaurin series for the sine function does have a linear term. It's x to the power 1 divided by 1 factorial. And then the rest of the non-zero terms for this Maclaurin series are the same as what I've written up above. Minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So I almost have the sine function, except I'm missing something. I'm missing this x. Okay, well, what will I do to fix this? If I'm missing an x on the right, I can just subtract. And to keep both sides of this equation balanced, I will subtract x from both sides of the equation. So this tells me that sine of x minus x, that's definitely a function, and its Maclaurin series should be exactly what I had in sigma notation at the start of this problem. Now, why can I subtract individual terms of this power series and still have a coherent result? I do need to be careful about using these operations when it comes to infinite sums, because these involve limits, and limits sometimes break our more intuitive notions of algebra. Well, this is all fine because the Maclaurin series for the sine function converges for all real numbers. So as long as this power series is convergent, it will be absolutely convergent using choice of the root test or the ratio test. And I can move individual terms in or out of the sigma notation. So here is my answer. This series right here is the Maclaurin series for sine of x minus x. If you don't feel justified just yet, well, I applaud your mathematical rigor. But just to be extra careful, let me calculate derivatives of this function sine of x minus x. Well, the number 0 derivative of sine of x minus x is the function sine of x minus x. The first derivative of this function is cosine of x minus 1. And notice When I plug in x equals 0, that will give me, this is my f prime of x, that will give me the numerator for my linear term in the Maclaurin series. Cosine of 0 is 1. I subtract 1, I'll get a numerator of 0. So for that reason, the Maclaurin series of this function does not have a linear term. Or you could say the linear term has a coefficient of 0. As I continue, the second derivative of this is going to be minus the sine function, and the derivative of that minus 1 will be 0. So at the second derivative, I get exactly what I would have gotten for just the sine function, with no subtraction by x. And for the third derivative, the fourth derivative, the fifth derivative, and so on, I'll have exactly the same formula that I would have seen for the unchanged sine function. So this Maclaurin series is going to completely agree with the Maclaurin series for the regular sine function, just that its linear term has a coefficient of 0 rather than a coefficient of +1. Hey, that's exactly what I had written out when I computed those terms. So a little extra justification. That was the last example from the classwork that I wanted to work through. But if you've made it this far in the video, I have an extra treat. Now, what I'm about to do goes outside of our syllabus. I will be using an imaginary number. This is not something that I will be testing you on at the end of the term, but I wanted to give a demonstration of something that's really cool. So I'm going to be using the imaginary unit I for this demonstration. I is the number square root of -1. And it has the property, well, of course, that I squared is -1. I to the power 3 is then going to be, well, my mouse disappeared. Here we are. I to the power 3 will then be -I. I to the power 4 will then be +1, since it's the square of I squared. All right. Now, what I'm going to do with this is I'm going to look at what happens if I take e to the power I times x. For this demonstration, I'm leaving my variable x as a real number. X is confined to the real axis, and I'm multiplying it by this number I. Well, if I want to calculate this, let me use my Maclaurin series. I know that the Maclaurin series for the exponential function says that I have a constant term 1 over 1 factorial. I have a linear term, my variable to the power 1 over 1 factorial. Excuse me, I went a little bit, I should have said 0 factorial. Sorry about that. I'm getting ahead of myself, but of course, 0 factorial is equal to 1 factorial. So that mistake wasn't too damaging. I'm still glad that I caught it while I was explaining. The next term of the Maclaurin series, my denominator will be 2 factorial, and my numerator will be I times x all squared. Well, I'm going to square those things separately. When I square the number I get -1. And then when I square the number x, since x is a variable, I'll get x squared. Let's continue. For my third term in the Maclaurin series, I'll have denominator 3 factorial, and I'll be cubing my input, I times x. Well, when I cube the number I, I'll get minus I. When I cube the number x, I'll get x cubed. For the fourth term in my Maclaurin series, I'll have a denominator of 4 factorial. And this time, the fourth power of I gives me the number 1. So I'll have 1 times x to the power 4. And then the pattern is going to repeat itself in the numerator. The denominator is going to be 5 factorial, of course, but I to the power 5, well, this is the same as I to the power 4 times 1 more power of I. And since I to the power 4 is the number 1, I to the power 5 is the number I. This is one of the ways that imaginary numbers can get a little weird. Their powers can loop around like this that we don't usually see in the real numbers. Well, we do see this for the number -1, but that's a tangent. So my numerator here will be the number I times x to the power 5, all divided by 5 factorial. And of course, the Maclaurin series is an infinite sum if I want to have the exact value of this, e to the power ix. Now, at this point, I notice that some of these fractions involve imaginary numbers, and some of them don't. So I'm going to separate my fractions depending on whether or not the imaginary number I shows up. So the first fraction is just going to reduce to 1. The second is going to reduce to I times x. The third only involves real numbers. Again, x I'm treating as a real number here. So this will be minus x squared over 2 factorial. Then I'll have the third term here, also has an imaginary number in it. And what I'm going to do is I'll say I've got x to the power 3 over 3 factorial, and this is times minus I. I'll put it on the second row here. The next number after that, the next fraction, only involves real numbers. So I'll put that on the first line, x to the power 4 over 4 factorial, and then here plus I times x to the 5th over 5 factorial. Okay. Well, this first row should look familiar. If the pattern continues, the next one of these fractions should be minus x to the 6th over 6 factorial. And this seems to be spelling out the Maclaurin series for the cosine function. On the second row, where I've isolated all of the imaginary numbers, right, the next one of these would be minus I times x to the power 7 over 7 factorial. Well, each of them is multiplied by the imaginary unit I. So what I will do is I will factor that out. Kind of like earlier in my video, as long as the series converges, I'll be able to factor this all out. Each of them has that same factor of I. And when I factor it out, I see that I'm changing my signs, SIGN, from positive to negative and back. So this series in parentheses is actually spelling out the sine function, sine. So these Maclaurin series are telling me that e to the power ix should be equal to the cosine of the number x plus my imaginary number I don't want the serif on that. My imaginary number I times the sine of x again. E to the power ix equals cosine of x plus I sine of x. And this is a true fact that we can learn from power series. Now, I'm going to go one step further with this, because I know that the cosine and sine functions have special values depending on what number I pick for x. Now, it's a little bit of a stretch again, because I am evaluating my exponential function at an imaginary number. And because that's outside of our curriculum, I haven't really explained what this calculation would mean. But if you feel comfortable taking e to the power I times pi, I times pi will be an imaginary number because it involves the square root of -1. And this should be equal to cosine of the number pi plus I times the sine of pi. And actually, I know what both of those numbers are going to be. Cosine of pi is the number -1. Sine of pi is 0. And even though taking the square root of -1 might be a strange thing to do, I feel comfortable in saying that the square root of -1 multiplied by 0 gives me 0. So this tells me a very famous formula that you might have seen before. E to the power I pi equals the real number -1. So this is a very neat formula to me, that I have in it some of the most important constants that I've seen in mathematics. Pi, e, 1 shows up. I could even choose to rearrange this and say that e to the power I times pi plus 1 equals 0. This might be a version of the equation that you're more familiar with. So now I have some of the most important numbers in mathematics: 0, 1, e, pi, and the imaginary unit, the square root of -1. And on top of that, I have some of the most important operations in mathematics here. I have addition, I have multiplication, and I have exponentiation, all wrapped up in one neat relation. And again, we got here by applying this idea that I can represent a function by a power series and just trying to see what would happen if I put in a slightly different number. I put in the number I times x, and I rearrange, see if I can't get something neat.